All right, here's 6-5, day 1. We are in the trig form of a complex number. Let's see here, anything before we dive in? You might see some similarities with kind of this whole trig form with kind of the sine and cosine thing that we did with vectors in section 3. We're not going to go too crazy with this topic. More or less what we're after is let's know how to do the conversion from a complex number in standard form to trig form, and then to do a few basic operations. That's about it, though. All right, so let's do a little recap of what we call the complex plane. We haven't seen it since chapter 2. It's not a topic we really, we just kind of know the basics of it, but we don't really go crazy and do a lot of stuff with complex numbers. So, like right here, if we were to plot that number, it has a real component of 3 and an imaginary of 1, so that's where we would find 3 plus I. And let's say we've got 2 over to the left, 1 down. That's where we'd find negative 2 minus I. Okay? The first thing I'm going to show you how to do is to take the absolute value of a complex number. Okay? You've done that with real numbers before, and when you hear absolute value, I bet you think something like, well, if the number was positive, just leave it alone, and if the number was negative, just make it positive. And that's true when you're dealing with real numbers. That's an okay way to think about it. The actual definition of a number's absolute value is its distance from 0. Okay? That's really what it's all about. So now if we relate this to a complex number, we're not going to change the definition one bit. It's still a number's distance from 0. So here we have our complex plane. Here's the real. Here's the imaginary. And then let's just say, here we are, right there. A plus BI. So A is the number comes first. That's the real component. B is the imaginary. So there's A and B. The absolute value of that number, okay, notice I've just named this complex number Z. Its absolute value is right there. The definition doesn't change. It's just its distance from 0. You probably notice here it's starting to look a little bit Pythagorean theorem-ish. That's kind of exactly how it plays out. So as long as you know A and B, it really just fits the Pythagorean theorem, and you can get that distance from 0, which is the number's absolute value. Let's head down here and plot one and then get its absolute value. So as always, here's our real number line, and again, that's where we, for the topics that we've studied in Precalc, that's where we spend most of our time. We've just kind of been aware that, from the square root of -1, there's this whole imaginary plane to kind of complete the whole number system, but we're just kind of familiar with it, and we don't use it a whole heck of a lot. All right, so -2 plus 5i there it is. And again, all we're after on this slide right now is that complex number. What is its absolute value? A is -2 and B is 5. If we wanted to leave it exact, it would be the square root of 29. Okay, not too terrible. Okay, so now what I'm going to show you is, the reason I'm doing that, or showing you this stuff, is that's a part of making this conversion of, a complex number in what we would call standard form. And anytime you hear me talk about standard, you can think of A plus BI, right? The only form we've ever seen a complex number in before. So now let's just say right out here that we've got some complex number. Here's its real component. Here's its imaginary. Okay? So we're going to switch here. It's kind of just the way that we're describing it. As we've seen complex numbers, we would say, all right, what's the real component? What's the imaginary? And there you go. Okay? The absolute value part you will see us refer to as R. Okay? You've seen how to find R. Okay, that's the absolute value. The other thing we got to be able to do is to find the angle that complex number forms with the x-axis. Okay, the whole idea behind a trig form of a complex number is to describe it in terms of r and theta, not a and b. Okay, to describe it in terms of r and theta. You have essentially already seen on the previous slide how to get r. That's the whole absolute value thing. So now, try this. Okay, based on that diagram, we've seen this before. This is a right angle right there, so the cosine value of theta would be a over r, or it would then follow that a is r cosine theta. Also, sine of theta would be b over r, or the value of b, that's the imaginary component of the number, would be r sine theta if you just rearrange that equation. All right, so now we've got these expressions to substitute in for a and b. For a, that can become r cosine theta. B could be r sine theta times I. Okay? Now, you'll come across this. That's typically not like how you're going to see the number written. Because notice how we're writing r twice. It's not real common to see that. You'll usually see r once out front. And then you will see cosine theta plus, and then they switch the I to be in front of sine, I sine theta. Okay? So that's typically what you're going to see when you're talking about the trig form of a complex number. Now that's all great. We got our formula and looked over a definition there. But let's do it. Okay, we have a number right here. Complex number. Negative 2 over. Negative 2 square root 3. It's like 3.5. So there it is. That's z. Okay. And now what we're after here is twofold. First, we're going to find r. How far is that complex number from 0? And then, right here, we're going to find theta. Okay? We have a and we have b. That's negative 2 and then negative 2 square root 3. Typically, you'll want to start with r just because between r and theta, it's the easier of the two to find. Just doing a little number crunching here. Okay. Whoops. Getting a little carried away. That's all we need there, which after you square it would be 4 times 3. That square root would cancel with the squared. That would be 12 plus 4, or 16. Square root of 16 is 4. And there's R. Okay, there's R. So now here's what we have on our diagram. We got a lot of information here. Okay, we know this side is -2. This side is -2 square root 3. And we just found that R is 4. To get our angle, essentially what we need is an inverse trig function. Okay, but you have some options here. Really, any inverse trig function that you want to use, because you have all 3 sides of this triangle. I'm going to use inverse cosine. Okay, that would be -1/2. Which you might recognize on the unit circle at 4 pi over 3, or if you want to get it in degrees, that would be 240 degrees. Okay? So final answer for our complex number z. R is 4 times, for the real component, it would be cosine of 4 pi over 3 plus I sine of 4 pi over 3. Okay? Anytime you're seeing that trig form, think R and theta, right? We have A and B, we want R and theta. All right, one more here. This is actually probably the easier case. We're going to do the opposite. We have given to us a complex number that is written in trig form. Okay, here's what we know. It's down here somewhere. It's in quadrant 4. I can tell that because our angle is -pi over 3. And then R is the square root of 8. Okay? What we are after is to figure out here and here. What's A? What's B? That's the switch that we want to make. Okay? So what I'm starting with right here is, and in the unit circle you could look at 5 pi over 3. Okay, but cosine of that angle, and if it wasn't on the unit circle, we could just plug it into a calculator. But that's a half. So I'm going to substitute that value in, plus I do the same thing at 5 pi over 3. The sine value is -√3 over 2. Okay? And from here, it just becomes a simplifying game. Square root 8 can actually simplify to 2 square root 2. And now it becomes basically like a distributive property. And I get 2 square root 2 over 2 minus 2 square root 2 times square root 3 over 2, and of course that is with I, Those will cancel there. Square root 2 times square root 3 is square root 6. And so a would be square root 2, b would be negative square root 6. I've got this switched over to standard form.